So in this talk, I will present some recent work, which shows how some recent breakthrough in computational methods allow to shed new light on the slow dynamics of supercooled liquids. So this work was done in collaboration with Benjamin Guiselin and Ludovic Berthier from the University of Montpellier. So the physics that I'm interested in is the transition from a fluid state to a disordered solid. And this is actually quite a generic phenomenon, which is relevant to describe a variety of materials. And for example, yesterday we heard talks from Domenico and Jost, who showed that densely packed colloids can form an arrested disordered solid, which is a glass here. And this week we heard also a bit about biological or active matter. And to me, these densely packed cells are actually disordered systems, and they form tissues that you can see here can be solid and squished between two plates. And in all these examples, actually, by compressing or cooling the system, its dynamics becomes increasingly slow, and eventually the system falls out of equilibrium and becomes stuck in an amorphous solid. So if you look at the simplest system, for example, molecules in an experiment, or soft particles as a model for atoms or molecules, we get the following phase diagram. So by cooling fast the liquid, instead of forming an ordered solid here, the liquid remains disordered and enters what's called the supercooled liquid regime. So here, the liquid is still in thermal equilibrium, but it's metastable with respect to the crystal. So as the liquid is cooled, on the right, you can see that its relaxation time, so here the log of the relaxation time, as a function of the inverse temperature, increases dramatically. So the liquid slows down as the temperature decreases. So the typical time scale for molecular motion increases from around 10 to the minus 10 seconds in all these sorts of molecular liquids, up to 100 seconds, which defines the glass transition temperature, which I will refer to as Tg. So below Tg, the relaxation is simply too slow, and liquid falls out of equilibrium and transforms into a glass, which is a disordered arrested state. And the main question here is really to understand what drives this dramatic slowdown at the microscopic scale. And in order to understand and maybe rationalize why the dynamics become so slow, a natural step would actually be to observe the dynamics when it's really slow at the microscopic scale, and to look at how particles move close, for example, to Tg. So various experimental or computational methods may achieve this. And for example, atomic or molecular liquids can be studied by experiments, and we can really reach this experimental glass transition. However, they can only measure averaged or macroscopic quantities, and observing the individual motion of the molecules is impossible for now. So we know that the dynamics is slow, but we don't know in practice how the molecules are moving. So using standard microscopy techniques, we can use colloids to study this glass transition, and we can actually track the individual motion of the particles. But since they are large compared to atoms, this means that the microscopic timescale are much longer. And as a consequence, we can only probe the equilibrium supercooled liquid in a much shorter time window, and we can only probe the first 4 or 5 decades of dynamic slowdown, which is actually 8 decades away from the experimental glass transition we're interested in. So similarly, computer simulations can have microscopic resolution, but they're also much less efficient at running the physical dynamics than nature. And with great effort, we can run around 10 to the 9 molecular dynamic steps, which allows us to probe around 7 decades in this dynamical slowdown. And if we consider that this tau zero, the relaxation time at the onset temperature of glass dynamics, is 10 to the minus 10 seconds, this is equivalent to simulations which would be of around 1 millisecond. So this is much shorter than the 100 seconds that are observed in molecules. So here I introduced this temperature scale, TMCT, which is for mode coupling transition temperature. And the only thing that you need to know about this temperature is that it actually delimits the temperature regime, which is accessible by colloids and simulations. So in the end, the short answer is that despite a century of studies on glasses, we still don't know how the molecules move close to TG. And yet this is key to understand why glasses form. So we still know something, at least from these experiments, and let's first look at the experimental measurements that are available. So thanks to dielectric spectroscopy, we can probe molecular motion at average scale, but we can probe that on a very large frequency scale here over more than 14 decades. So on the right, this is the relaxation, the dielectric relaxation spectra for various temperatures from the onset of glassy dynamics down to the experimental glass transition. And you see that in this representation, the 12 decades increase in the relaxation time actually transposing into a 12 decades shift to lower frequencies of the spectrum. What you see is that this overall shift is also accompanied by an equivalent broadening of around more than 12 decades. And at the glass transition, you see that the main peak here, which is actually usually considered as the interesting phenomenon, extends much higher, at much higher frequencies here. And the signal is actually well fitted by a power law. It's found at intermediate frequencies or relatively short timescales, and its amplitude is around 1% of the main peak. So this is in excess of this fit of the main peak, and this is why this is called the excess swing. So this is quite a generic feature. It's observed in many molecular liquids, also metallic glasses. And there are many models or fits to explain the origin of this signal here, but the truth is that we actually don't understand its origin. And this simply reflects the fact that we do not know how the molecules move close to the glass transition temperature. So in the following, I will show that this is now possible thanks to computer simulations. So while these computers are much less efficient than nature, they're extremely flexible, and one can develop smarter algorithms to sample equilibrium configurations. And this is precisely what the so-called swap Monte Carlo algorithm does, which combines standard molecular dynamics simulation to swap moves where you exchange the radius of two particles, and this works in polydisperse systems. So here on the left, I show the relaxation time in blue with standard molecular dynamics, and the limit above which we cannot run simulations. So if we extrapolate this relaxation time to 12 decades, this locates the experimental glass transition we're interested in. And we see that by adding swap moves, the dynamics is much, much faster. And the speed up is such that we can actually achieve equilibrium at the experimental glass transition and below, thanks to this algorithm. So by taking these equilibrium configurations as initial conditions for standard physical dynamics, we can now probe the physical dynamics of supercooled liquids over 1 to 10 milliseconds, so the limit for computer simulations, but we can do that down to the experimental glass transition. So we follow this strategy and observe the equilibrium relaxation for as long as possible, so a few weeks or months, actually during most of the pandemic, down to the experimental glass transition. So we monitor the dynamics via this function, which is a self-intermediate scattering function shown on the left, which basically quantifies the correlation of one particle's position over time. So you see it starts from 1, and then eventually when the structure has relaxed, it goes to 0. And I show the curves only in the temperature regime, which has been so far unexplored, from MCT down to the glass transition. And of course, here the dynamics is as slow as expected. So you see that after more than 9 decades in time, the structure is still almost completely stuck and the correlation function almost plateaus. So to compare with experiments, we compute dynamic susceptibility, which is shown on the right here, which actually has a shape which is similar to experiments. So at very high frequencies or short times, we have a peak, which corresponds to a very simple vibration of the particle in its cage. And then at later times or shorter frequencies, we have a main relaxation peak shown here, which is visible in the frequency window that is accessible by simulations, but eventually as temperature decreases, it shifts to the left, just like in experiments. So at high temperature, we can directly fit this peak shown in dashed lines here. And at lower temperatures, we can extrapolate its location, and we do that in a very safe way. So this is a good estimate for the main peak. And what we see is that close to the glass transition, as temperature decreases, the data always lies above the extrapolated fit. And eventually, at the glass transition temperature, the signal is well fitted by a power law here. It's found at intermediate frequencies, and its amplitude is around 1% of the main peak. So the conclusion of our simulations is that this excess swing, which is a very generic feature of glasses and which is poorly understood, is actually well observed in simple models of spherical particles. So it's something quite generic also in these systems. So computer simulations allow us to go one step further and actually to directly see the microscopic motion, which is giving rise to this signal here. So here I show some snapshots of a simulation which are logarithmically spaced in time from the very beginning of relaxation, so around 3 decades before the main peak, up to the alpha relaxation, which I call tau alpha. So the particles in the snapshots are colored in red if they have relaxed, so the local environment has reorganized, or in blue if they have not. So what we see in these snapshots is that the relaxation starts actually very early compared to the main relaxation, and starts in localized and quite rare clusters as shown here. And you see that between the first two snapshots, the relaxation is driven by the apparition of new clusters, for example, this one here or this one there. And as time increases, eventually between the two last snapshots, you see that relaxation proceeds by the growth of the existing relaxed clusters, which are in red. So here you see that it has grown a little bit. So in the following, I will explain why this picture, which has been revealed by these simulations, actually can explain the asymmetry of the spectra and also explain the excess swing. So just to give you an idea, these simulations are performed at quite low temperatures. So their relaxation time is around 30 milliseconds, which is quite low for simulations. And at much lower temperature, we still see close to CTG, these sort of initial relaxed cluster, and they become increasingly sharp. So to begin, let's focus on these early times at which the excess swing is observed. So if we look at the times at which these clusters start to appear, as evidenced here, which I call tau, and we look at the distribution of timescales over which new clusters start to appear, we get the following data here. So in order to compare different temperatures which have different overall relaxation times, we normalize the times by this relaxation time tau alpha, which is around here. So at high temperature, so in the typical temperature regime, which is accessible by simulations, we see that already relaxation starts 4 decades before the main relaxation time here. And as temperature decreases, we see that the distribution broadens to lower values, which means that the relaxation starts very early, right from the start. And eventually, close to the glass transition temperature, we see that the data starts to collapse onto this power law. And this power law is actually the same value as the value that I showed in the relaxation spectra. So we understand that the excess swing, so this power law shape in the spectra, is actually directly explained by the apparition of new relaxed cluster at very short time scales. So this explains the microscopic origin of the excess swing, and we understand that it's simply due to the very rare and localized relaxation of some regions in the system. So this explains the excess swing. However, we now have to explain why this power law in the spectra doesn't continue, let's say, to much lower frequencies. and why eventually it transforms into a sharper peak. And dynamic facilitation is actually key to answer this question. So here in this snapshot, I show the particles which have relaxed after a long time scale. And the particles are colored depending on the time at which they have rearranged. So the particles which relax very early, which are the clusters that I talked about before, are colored in red, and you can see that they are sparse and quite localized here. And the particles that have relaxed at later times are colored following this color code, so going from orange, yellow, and then eventually after 3 decades, the particles that relax much later are shown in blue. And the black zones are actually regions of the sample which have not yet relaxed. So what we clearly see from this snapshot is that relaxation starts into these small clusters and then eventually spreads throughout the sample because you can directly read the color code from the configuration here. So what we see is that relaxation in one part of the system at a given time helps relaxation of neighboring particles at a later time. And this is precisely what we call dynamic facilitation. Also, and most importantly, these regions here, which have not relaxed, always relax thanks to dynamic facilitation. So they're basically invaded by the color code and eventually shrink and relax thanks to their neighbors. So this can explain why we get a much sharper peak at low frequencies, because by combining these observations, so relaxation which starts at very localized regions and then that increases with time, we get the following picture. So the picture that we have from these numerical simulation is that the liquid is really disordered. So there are very different structures or underlying quantity, which may be thermodynamic. At this point, we do not specify that. So the dynamics is really heterogeneous. Some parts of the system will relax very, very fast, and some others will take incredibly long times to rearrange. So this gives rise to a very broad distribution of relaxation times. And in terms of relaxation spectra, this gives rise to a very broad spectrum here. And I don't even show the maximum, which is outside the relevant frequency windows for experiments. So we have this huge distribution of relaxation time. And what happens is that we also have this dynamic facilitation mechanism, which implies that all the sites that are relaxing very fast are actually helping their neighbors, which may be actually much slower, to relax. So this means that the very long time scales in the distribution of relaxation times are cut. And this means that all the signal which should correspond to very long time scales are cut and actually form this much sharper peak here. So this is a quite provocative picture because in this picture, which is actually supported by numerical observation, it's rather the main peak, which people think is the interesting phenomenon, which is in excess compared to this underlying distribution. But we also understand why, if you look at the data which corresponds to the system with dynamic facilitation, which is actually the case in molecular liquids, you understand that if you fit this peak with this dashed line, for example, you have the impression that there is some signal in excess which you don't know the origin of. So thanks to these numerical observations, I was able to actually devise a very simple model which gives rise to this spectra. And it actually corresponds qualitatively very well with glycerol or many other molecular liquids. And this is really nice because we now understand what may be going on and these short time scales. And we understand that this is really the important part of the relaxation, and we should understand it better. So to conclude, so the relaxation dynamics of supercooled liquids can now be probed in simulations close to the experimental glass transition. And I think that this paves the way to new computer studies because, I mean, this is only the beginning. So there are many new things to explore in this regime, but also to trigger some theoretical developments because these models should account for these effects, which are really local. And maybe Valentina will talk about activation, and this is really hard to capture theoretically, and this is what we see in the numerical simulations. And I also hope that this will trigger some new experimental studies, for example, in single molecule experiments, in order to be able to actually see our scenario in experiments. And with this, I thank you for your attention.
Thank you very much, Camille. Very nice talk. So it's time for questions. The first is Thomas. Thomas, please.
Hey. Yeah, hi. Really cool work and really great way to pivot out of a pandemic. That was just really fun. So if I understand, you're currently using SWAP to generate a big ensemble of systems that you're then just brute forcing all of them at the same time to get good statistics. Is that right?
Yes, that's correct.
So I guess my question is, do you think there's any hope or possibility that now that you have all of this dynamic data, to take some of what you know about how the particles relax and use that to accelerate, use a SWAP-like algorithm to study dynamics by like accounting for the Monte Carlo acceleration somehow?
Yes, I mean, yeah, I would love to do that. I think that's, one possible direction for what I mean by these future studies would be, I mean, one thing that I have in mind would be to actually use the data to, well, to be trendy. For example, machine learn the type of relaxations that, okay, I see that we're on the same wavelength. To learn, the type of motion that's occurs spontaneously in the physical dynamics, and to maybe, instead of doing swap moves, for example, to instead of doing very simple translational moves, to propose elaborate or adapted moves, which may be more collective, to speed up the physical dynamics. Yes.
Okay, very cool. Nothing wrong with being trending if trendy gets us funded.
Exactly. Yes. Yes. Yes.
Okay, next question, Pierfrancesco.
Hi, Camille. Thanks a lot for the talk. I just have a preliminary question that is, what's the polydispersity that you use?
So this one is quite polydispersed. So it's the one with its continuous polydispersity with 20%. So it's quite polydispersed. Okay,
but then, I mean, I could think that the continuous polydispersity that you are by hand introducing in the system has naturally a lot of very, very soft spots that you eliminate, but they will be there. So how can you be sure that the power law that you see is just given by is not on sorry, how can you be sure that the power law that you see is it's not there? I mean, it's there, at least a part of it, just because you have used this monster of polydispersity that you have, and maybe it has also some other things that are there. Do you have a smoking gun for that?
Oh, my smoking gun is that I'm basic. I mean, I think that this is really the case, that it's due mainly to disorder. But since I have this doubt and I want to get rid of it, I'm actually doing the same in ternary models. So, I mean, it's a Cobb-Anderson model with a very slight proportion of third types. So it would be a ternary model for which, I mean, people have used binary models forever and no one ever complained about how this would be relevant for classes. So I'm doing the same in the ternary model, and the preliminary results show that this mechanism is actually really robust, but I will be able to tell you in a short time. And I mean, trying to see if among computation models, this is universal, I think is the next step.
Okay.
But I think it is, I mean, the results show that it is, yeah.
Okay, thank you.